I am Jismeri Jose, Faculty of Department of Mathematics. It's my privilege and honor to host the fourth day of the International Webinar Series on various fields in mathematics organized by the Research and Postgraduate Department of Mathematics in association with IQAC, Maharaja's Government Autonomous College, Ernakulam. Today, we have with us Dr. Shery Fernandez, Associate Professor of Mathematics, Cochin University of Science and Technology, to give a talk on approximation and optimization in Hilbert spaces. Now, I would like to invite Dr. Sucha TV, Associate Professor of English and Council Secretary of Maharaja's College, to speak a few words. Please, ma'am.
Good afternoon to all. Honorable Head of the Department, Convener of the webinar series, and my dear friend Dr. Bloomy Joseph, Distinguished Speaker of the Day, Dr. Fernandez, Coordinator of the webinar, and my dear friend Professor Jismeri Jose, all faculty members of the Department of Mathematics, participants of this webinar, scholars from various colleges, and my dearest students. At the outset, let me express my boundless happiness and thanks for giving me this opportunity to address you, to meet you. Because happiness is always meeting people, which we especially have come to realize during these pandemic days. We are ourselves a whole lot of brave hearts who have endured consequent years of natural calamities like flood, landslides, and now it has come to the 2020 pandemic. Every experience is different, more deadly, and more challenging. To continue to live through these times and come out healthy and alive is the greatest goal. All through these times, we know that our jobs, that of teaching for we teachers and learning for you students, have never come to a standstill. Education really becomes a balm, a medicine, a support system for a healthy living and a wise kind of enduring through these times. So it is at this juncture, during this goodbye month of December, during this wintry month, our college celebrates the spring flowering of diverse webinar series in various departments, unfurling very curious, interesting topics and eminent speakers from all over India and abroad. They just come to visit us online in the virtual platform. And we just have interactions, deliberations, and we just acquire knowledge through this. So it is indeed a happy and worthy time for we at Maharaja's. At this time, I wish to speak to you something about knowledge. According to German philosopher Habermas, there are 3 levels of knowledge. The first one is analytical and empirical knowledge, which you gain through observation and experience. And we learning mathematics, we just gain so much knowledge from the textbooks, from the experience of doing problems and all these things. And we know that this is the era of information revolution. At the click, at our fingertips, lots of information are there. We can just gather the information and we can just become walking Wikipedia. But that is not what is expected out of students. We acquire knowledge, we can master in so many quiz programs, but that is not what is really needed out of us. The next level of knowledge that Habermas said is a hermeneutic historical knowledge, That is, from the knowledge that we have gained, we should be able to interpret the things that go on around us. We should be able to detect, we should be able to interpret that, and we should be able to understand that. That is very, very important. And then comes the level of critique and dialectical knowledge. That is where these kind of webinars count. From the knowledge, we just interrogate, we dissect, and we detect, and we produce knowledge for posterity. We have lots of experience, as I told you at the outset. We are a generation who are blessing or a boon or a doom, we don't know, but we have great lots of experience. So from this experience, we have gathered lots of knowledge, and we know how the youngsters rose to the occasion, and with the techno-savvy work, how they helped us out of the flood situations. We really salute our youngsters, and we saw how the ordinary fishermen really came out as our saviors. So from all this knowledge, we should really be able to produce knowledge for posterity. So our knowledge should not be just remaining in the ivory towers of wisdom. We should look around us. Now, we are the greatest democratic country, and today we know how we celebrate democracy today. And what all things happen around us, we should have a great knowledge about it, and we should really be able to interact with this. And with the knowledge that we have, we should be able to contribute to the society. Social commitment is always a signature of Maharaja's courage. And with your knowledge, how are you going to contribute to our society? How with your presence, how this world is going to become all the more beautiful. That is what we really want to think about. And always I feel that when you learn complex things, try to make them simpler and try to translate them to people and make your subject popular among people. So be beautiful, do beautiful, think beautiful, and let the world be all beauty and light. Let us be very, very optimistic about our future. And this is the fourth webinar of your webinar series. I understand that you people are having a very fruitful time for very many important deliberations. And I wish you all success, and let every participant who is engaging the precious time with this webinar get the most out of it and shine on and spread that light to all around. Thank you. Thank you so much.
Thank you. Thank you, ma'am, for your nice words. I cordially invite Dr. Blomi Joseph, our head of the department, to formally introduce and welcome our invited guest, the key speaker of the event. Please, ma'am.
Good evening to one and all. A brief description about our resource person, Dr. Shery Fernandez, Associate Professor, Department of Mathematics, Cochin University of Science and Technology. Around different positions like subject expert, MG University, academic council member, secretary, board of studies, NSS coordinator, research club coordinator, etc. Done minor projects on solutions of traffic jam problem through fuzzy applications, study of antibacterial effect of nanosilver and dose optimization through fuzzy mathematical techniques. He has got Best Paper Award in International Conference on Methods and Models in Science and Technology, Chandigarh, India. Published many papers in national and international journal. Expertise in representation theory, mainly G-module theory, fuzzy mathematics, applications, etc. His inputs and contributions were always a phone call away. On behalf of all, I welcome you, sir, for the presentation.
Thank you. First of all, I thank Dr. Bhumi Joseph, the head of the Department of Mathematics, and each member of the team behind this international webinar for this opportunity. So I start my presentation now. Is the screen visible?
Yes, sir. It's visible. Yes.
My topic is approximation and optimization in Hilbert spaces. So,
Sir, please switch on video.
okay, 1 minute.
Okay, sir. Now,
So definition of space. Let X be a vector space over the field K. So in this talk, throughout, K is either the field of complex numbers or the field of real numbers. And an inner product on X is a function from X cross X into K. For every vectors X, Y, Z in X and K in K, it satisfies the following conditions. First one is the positive definiteness. That is inner product X greater than or equal to 0, and it is equal to 0 only if X equal to 0. And linearity in the first variable. That is with respect to the first component, it is linear. And conjugate symmetry. That is inner product XY conjugate equal to inner product YX. An inner product space is a vector space together with an inner product on it. And a complete inner product space is called a Hilbert space. Some remarks. All inner product spaces are normal spaces. Not all normal spaces are inner product spaces. So let X with this inner product be an inner product space. Then the function defined on X by norm X square equal to inner product XX. That is this function norm defined in terms of inner product. Then it satisfies all the properties of a norm. So it is a norm on X. So the vector space together with this norm, a normed space. So all inner product spaces are normed spaces. Therefore, all complete inner product spaces are complete normed spaces. So all Banach spaces. And all inner product spaces X satisfies the parallelogram law and Schwarzschild inequality. That is, if X is an inner product space, then any two elements of X satisfies parallelogram law. That is, this is the norm induced from the inner product, norm X plus Y square plus norm X minus Y square equal to 2 times norm X. And this is the Schwarzschild inequality. Mod inner product XY square less to norm X square into norm Y square. Next is some of the examples of Hilbert spaces. So I am considering only 3 which I am using in this presentation. First one is Kn, the set of n tuples of scalars. We define inner product on H cross H by this inner product equal to sigma j equal to 1 to n X of j, Y of j conjugate. Then it is an inner product on H, and since K is complete, H is complete, so H equal to Kn is a complete inner product space, so it is a Hilbert space. Next Hilbert space is H. It is the sequence of scalars with sigma mod X of j square is finite. So we defined inner product as in the case of there it was the sum is finite and here it is infinite. Then we can show that it is also an inner product on H. And since LP is complete for any P, for 1 less than or equal to P less than or equal to infinity, H is complete. So it is a Hilbert space. But LP with 1 less than or equal to P less than or equal to infinity is a normed space. But the only LP which is a Hilbert space or an inner product space is LP with the P equal to 2. That is, LP with the P not equal to 2 is not an inner product space. For considering two vectors x and y in LP, 1 1 0 0 etc. Y is 1 minus 1 0. Then x plus y is this one and x minus y is 0 2 etc. And by using the definition of norm P on LP, we get or we can find norm P x equal to norm P y equal to 2 raised to 1 by P and norm P x plus y, and it is equal to norm P x minus y equal to 2. Then the parallelogram law holds only for x P equal to 2. So LP with the P not equal to 2, not a Hilbert space or not a inner product space. Now we consider x equal to C of AB, the vector space of all scalar valued continuous functions on closed interval AB, with the inner product defined by inner product xy is equal to integral a to b x of t y of t bar dt. It is an inner product on X, and all inner product spaces are normed spaces, and the norm induced from this inner product is this one. But in this norm, the space the C of AB is not complete. So what we do is we use completion theorem to make this inner product space a complete inner product space. So by completion theorem, there exists a completion of C of AB, and it is L2 of AB. This is the statement of completion theorem. For any inner product space X, there exists a Hilbert space and an isomorphism A from X onto a dense subspace W of H. And here X equal to C of AB. Then X is isomorphic with a subspace W which is dense. So C of AB is dense in L2 of AB. That is, C of AB closure is equal to L2 of AB. So this is the completion of C of AB. And L2 of AB is also a Hilbert space. So it is the collection of all square integrable functions. So by the definition of inner product xy equal to integral a to b xy bar dm is an inner product, and the norm induced from this inner product is this, and in this norm L2 of AB is complete. So it is a Hilbert space. The preceding case, we consider L2. Here L2 is the only Hilbert space like that. Here if we consider LP of AB, then P equal to 2 is only the Hilbert space. Where P not equal to 2, it is not an inner product space. So this is the definition of norm P on LP of AB, this one. And if we take x of t as t and y of t as 1 minus t, then their sum is 1, difference is 2t minus 1. And by using this definition, we get norm P x square, norm P y square equal to 1 by P plus 1, the 2 by P, norm P x plus y square equal to 1, and norm P x minus y equal to P plus 1 by P plus 1, the power raised to 2 by P. Then the parallelogram law, because if it is an inner product space, the parallelogram law holds. But in this case, the parallelogram law holds only if P equal to 2. So LP of AB with the P not equal to 2 is not an inner product space. Only 3 Hilbert spaces Kn, L2, and L2 of AB. Definition of an orthonormal set. A subset E of an inner product space is orthogonal if inner product of any two distinct elements is zero. And that subset is called orthonormal. First of all, it is orthogonal, and if the vectors are the same, then inner product must be 1. That is, inner product xx1 for every x in E, and inner product xy equal to 0 for any two distinct elements in E. Then Gram-Smith orthonormalization process. So if we have a linearly independent set in an inner product space, then we can form an orthonormal set u1, u2, etc., such that span of u1, u2, etc. is equal to span of x1, x2, etc. So method, first we take y1 as x1, then y1 by its norm, then y2, y3 like this, then un is yn by norm of n, then it satisfies the condition. This set satisfies the condition of an orthonormal set, and from the formation itself, it is trivial that a span of u1, u2, etc. is equal to span of x1, x2, etc. Now come into our topic, approximation and optimization. Let X be an inner product space and E be a subset of X, and X is an element in X. Then an element Y of E is said to be the best approximation from E to X. That is the subset of X, then the best approximation from the subset E to a vector X in X is Y if Y satisfies this inequality. That is, norm of X minus Y is less than or equal to norm of X minus Z for every Z in E. So by using this inequality, that is, norm of X minus Y is the minimum of all such norms. That is, norm of X minus Y is the minimum, infimum of norm of X minus Z, where Z in E. And from the definition of Z, a distance from E of a metric space into a vector, an element X in X is distance X equal to this one. So norm of X minus Y is infimum norm X minus Z, where Z in E, it is equal to distance of X minus Z. So if this Y is the best approximation, then norm of X minus Y is distance from X to the vector X. Then rewrite this approximation as an optimization problem. That is, optimizing, this is the set. So optimize, minimize norm of X minus Z subject to Z is an element of E. For example, if we consider the Hilbert space X equal to Kn, and we take E as a subset of Kn with components Z2, Z3, etc., Zn are all 0. Then trivially E is a closed subspace because it is a span of a finite set, so it is closed. And if we take, or if we fix an element X in X, the best approximation from this E to this vector. And from the definition, if Y in E is the best approximation from E to X if distance from E to X equal to norm of X minus Y. So we write the definition, distance from E to X, and it is the infimum of X minus E, norm of X minus E, where is Z in E. And from the definition of norm 2 on Kn, it is sigma j equal to 1 to n, X of j minus modulus of X of j minus Z of j square the whole raised 1 by 2. Where is that in E? So here I separate the first term from this sum. So it is X of 1 minus Z of 1 square plus sigma, because from second term on Zj 0. So X of j minus Zj of j is X of j itself. So we get sigma j equal to n mod X of j square. So this is infimum of this the whole raised to 1 by 2, where Z ranges over E. So we have here X is a fixed vector. We are going to find the best approximation from E to X. So this term is fixed because Z ranges over E. So what is the least value? What is the infimum of this sum? Now this is fixed, so that depends on the, and the first term is modulus. So what is the least value of the modulus? It is 0. So when this becomes 0, we get the infimum. So this is the infimum. And when this becomes 0, only if X of 1 equal to Z of 1. That is, Z in E is the, or Y in E is the best approximation from E to X, then Y is an element of E with the first component as the first component of the vector x. That is, first component is x of 1, 0, 0, etc. That is, this is the n tuple in E. So y in E is the best approximation from E to x. This is obtained directly from this definition. Now, we consider some theorems. Now, we are going to find what subsets of an inner product space has best approximations. So, first statement, let E is a subset of x and x is an element of E bar. Then there exists a best approximation from E to x if and only if x is an element of E. So, here what we take this element from E bar, E closure. This happens only if x is an element of E, means E closure is a subset of E. Really, we have E is a subset of E closure. That means E is closed. So the best approximation from E to x exists. This statement says that the best approximation from E to x exists only if E is closed. Second, there exists at most one best approximation from E to any x in x. So if it is closed, then there exists a best approximation. And in addition, if it is convex, then this statement 2 says that there does not exist more than one best approximation. There exists only one or maximum one approximation from E to x. And if f instead of subset, we are considering a subspace of x and x in x, then y in f is a best approximation from f to x if and only if x minus y is orthogonal to f. So this statement does not guarantee for the existence of a best approximation. It only gives one clue that if y is the best approximation in the A subspace, if f of a x, then x minus y is orthogonal or orthogonal to the subspace f. So this gives only one clue to find the approximation, best approximation. So these are the statements what I said. Now theorem 2. Let x be an inner product space and we have a linearly independent set x1, x2, etc., x1 and x in x. And if we take f, the span of this set, the linearly independent set, this set is finite. So f is a subspace of x of finite dimension, so it is closed. So if it is closed, then best approximation exists. Then the unique best approximation from f to this element x in x is given by y equal to k1 x1. So it is an element in f. So it is a linear combination of these m elements, but the scalars k1, k2, etc., km obtained from or are the unique solution of the normal equations. This one, that is in the product x1, x1, k1, x2, x1, k2, xm, x1, km equal in the product x, x1, etc. So this is a system of, here we are considering m vectors. So this is a system of m linear equations in m unknowns k1, k2, etc., km. And from the first part of the preceding theorem, we have if f is closed, there exists a best approximation. Since the unique best approximation exists, the system of m linear equations in m unknowns has a unique solution. And if k1, k2, etc., km are the unique solution, then the corresponding vector of f is the unique best approximation. And the distance we obtain from this equation. So this is the first statement. And second statement, here we are considering the linearly independent set with the m elements. Then if E is a subset of x in such a way that it contains the elements y in x with inner product y xj equals cj. Since we have m vectors in the linearly independent set, if we take an element y in x, inner product y x1, this is a scalar, let it be c1, y x2, y x3, etc., y xm equal to cm. So we get m scalars. So if you take an element with in such a way that the inner product of that element with the elements of the linearly independent set as cj, then the unique best approximation from E to x is y equal to to x. So y equal to x plus the linear combination k1 x1 k2 x2 etc. km xn, where k1 k2 etc. km are the unique solution of these equations. So here this system and the this normal system, these two are different. Here left sides are equal, but right side here it contains c1 minus in the product x1, cm minus in the product xx1. Then the distance is norm x minus y, and here by this equation it is norm of this element. So what we are going to do is by using the part A and part B, we optimize some problem. So first we use a part B. So this is the problem. Consider the optimization problem. Minimize integral 0 to 1 mod y square dm. So we have to minimize this subject to the conditions y in L2 of 0, 1. Integral 0 to 1 t y of t dm of t is equal to 1. And integral 0 to 1 t square y of t dm of t equal to 2. So by satisfying all these conditions, we have to minimize this integral. And we have here in the first condition is y in L2 of 0, 1. And L2 of 0, 1 means it is 2 integrable. And here a and b are 0 and 1. So y in L2 of 0, 1 means this integral exists. And we have to minimize that. So what is the minimum value? Since it is an element of L2 of 0, 1, minimum value is 0. So we need to find a best approximation to 0 from the set. E is the set satisfying all these properties, where E is the set consisting of elements in L2 of 0, 1, this integral equal to 1, and this integral equal to 2. So what we are going to do is we are going to make this to a problem or approximation problem in a Hilbert space. And here L2 of 0, 1 is the Hilbert space. So if we find the best approximation to 0 from the set E, where E equal to this, then that approximation is the solution of this, or optimal solution of this minimization problem. So we consider x1. So here we are using, I said we are using part B of the preceding theorem. So we take x1 of t equal to t and x2 of t equal to t square and equal to L2 of 0. And we have this set is linearly independent in this Hilbert space. X1, x2 is linearly independent in this Hilbert space. And from the definition of inner product on Hilbert space, what is inner product? Inner product on L2 of 0, 1. What is the definition? If xy in L2 of 0, 1, then we have inner product xy is equal to integral 0, 1 x of t y of t bar d m of t. So this is the definition of inner product on L2 of 0, 1. So if you take x1 of t as 1 and x2 of t as x1 of t is, I think it is t. x1 of t is t and x2 of t is t square. Then what is the inner product yx1? By using this, what is inner product yx1? It is integral 0 to 1 y of t x1 of t bar dm of t. So it is equal to integral 0 to 1 y of t x1 of t is t. So t dm of t. So this is inner product yx1. Similarly, what is yx2? We get 0 to 1 y of t square dm of t. And here in E we have integral 0 to 1 t y of t dm of t is equal to 1. So here we have integral integral 0 to 1 y of t dm of t is equal to inner product yx1. So this is the inner product on L2 of 0, 1. So we replace that by, that is, we replace this equation by inner product yx1 equal to 1 and this by inner product yx2 is equal to 2. So we can rewrite this subset E as elements in L2 of 0, 1 with y inner product yx1 1 and inner product yx2 2. So here we have. So now we can apply the apply part B of this theorem, because here what is E? E is elements in L2 of 0, 1 such that inner product yx1 is C1, that is 1, and inner product yx2 is equal to C2. X1, X2 is linearly independent. So we make the given into 1, which is in this form. So what we have to do? We have to find the best approximation from E for this subset E of L2 of 0, 1 to 0. And again, by using this part, we have to find these M linear equations in M and equal to 2. So we find 2 equations in 2 unknowns. We have to find all these inner products. So if we evaluate the inner product x1, 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 x2, x1, x2 is this, though x2, x1 is its conjugate. So it is a real, it is 1 by 4 itself, and x2, x2 is 1 by 5. Then part B of the theorem, the best approximation from E to 0 is to 0 plus x plus k1 x1 plus k2 x2, where the scalars are obtained from the equation inner product x1 x1 k1 plus x2 x1 k2 is equal to C1 minus. So the equations are inner product x1 x1 k1 plus inner product x2 x1 k2 equal to C1 minus inner product x1. Second equation x1, yes. I will try. So inner product x1 k1 plus inner product x2 x1 k2 is equal to C1 minus inner product x1. And the second equation, inner product x1 x2 k1 plus inner product x2 k2 is equal to C2 minus inner product x2. And here the vector x equal to 0, we are going to approximate from E to x equal to 0. So if we put x equal to 0 in these 2 inner products, we get the inner product 0, because we have in an inner product one component is 0, then the inner product is 0. So these 2, we eliminate these 2. So we get this equation. Then we substitute these values in this equation. So we get 1 by 3 k1 plus 1 by 4 k2 equal to 1, and 1 by 4 k1 plus 1 by 5 k2 is equal to 1. So the solutions are k1 minus 72 and 100. So theorem y equal to 0 plus k1 plus k2 x2 is the optimization optimum value or the best approximation. So if we substitute all these values, we get a y equal to minus 72 plus 100 t square is the best approximation. So this is an example corresponding to part B. Now we are considering part 1, an example corresponding to part 1. For we consider the least square approximation problem. The least square approximation problem can be treated as an approximation problem in appropriate inner product space. So here also we consider the inner product space L2 of AB. So let x be a scalar valued continuous function on AB, that is x is an element of C of AB. Find a polynomial P of degree at most m such that integral is minimum, or the value of this square integral is minimum. So here also we consider, we convert this problem into a problem in a Hilbert space, approximation problem in a Hilbert space. So here we take, here it is the scalar valued continuous function, so C of AB with the completion L2 of AB. And PM be the subspace polynomials of degree at most m. So what is the basis for this? It is 1, t square, etc. T raised to m. So here we consider m as 1 and a equal to -1 and b equal to 1. And we are going to find the approximation from a set that we define to x in L2 of AB. And here we take x of t as e raised to t. And AB are -1 and -1, so t ranges from -1 to 1. So first we consider m equal to 1. That is, it is the subspace of all polynomials of degree at the most 1. Then what is the basis? It is 1 and t. So we take P1. This is the subspace we are taking. P1 is span of x1, x2. Since it is finite dimension closed, so there exists a best approximation. And P1 is span of x1, x2. So this is this P1 as in that theorem 2a. What is 2a? A part. F a subspace which is closed, spanned by a linearly independent set. X1, x2, etc. xm. Here it is. Here in this case, it is x1 and x2, 1 and t. Then the unique best approximation is y, and k1, k2, etc. km are the unique solution of these normal equations. So here for finding the normal equations, we find the values x1, 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 x2, etc. Then we get two normal equations. The normal equations, and when we solve, we get k1 equal to e minus e raised to -1 by 2, and k2 is 3 e raised to -1. Then by the theorem, y equal to k1 x1 plus k2 x2 is the best approximation from the subspace. Here it is P1. Instead of f, here it is P1 to the vector x of t equal to e raised to t. And since this is this f is a polynomial of degree 1, so it is the best linear least square approximation. So it is the best linear least square approximation. Similar way, if we want to get the quadratic least square, best quadratic least square approximation, what we do is we consider the quadratic. To find this, we consider P2 as the span of, that is P2 as the polynomial set of all polynomials of degree less at the most 2. That is x1, x2, x3, 1t, t square. So we make the subspace f as P2 span of x1, x2, x3, and it is a linearly independent set. Also, we find already we found all these things. In addition, if we find all these values, then we get 3 linear equations in 3 unknowns k1, k2, and k3. Then if we solve these 3 equations, we get k1, k2, and k3. Then this is the q of t, that is y equal to k1 x1 plus k2 x2 plus k3 x3 is the best quadratic least square approximation from P2 to x of t equal to e raised. If we want cubic least square approximation, we make that P2 span of x1, x2, x3, x1, x2, x3, and x4. So where x4 equal to t raised 4 and so on. So by using 1, we get the unique best approximation of this problem, least square approximation problem. Now, next theorem. So in the preceding theorems, we were considering only inner product spaces. So from here on, we are considering a Hilbert space. So let H be a Hilbert space, and this is a linearly independent subset of H, and F denote the closure of its span. So closure of the span is span means it is a subspace. Closure means it is closed. That means F is a closed subspace of H. Since it is linearly independent by Gram-Schmidt orthonormalization process, we can orthonormalize this set. We get U1, U2, etc. An orthonormal set. And if we take Fm, the span of x1, x2, etc., xm, so it is a finite set. It is finite dimensional. So Fm is closed. And if we take Ym as corresponding to the orthonormal set U1, U2, etc., Un, this is the Fourier expansion. Ym equal to sigma in the product x un. So let Ym equal to this. Then this theorem says that this Ym is the unique approximation from Fm to an element in H. This is an element in H. So if Fm is the span of this and Ym equal to this, then this is the best approximation from Fm to X. And if this Ym converges to some Y, then Y is the best approximation from, unique best approximation from this F, closure of span of this set to X in H. So this is the theorem. So what we are going to do is, we solve the preceding exam in problem by using this theorem. So there we were considering the linearly independent set. So we were considering linear and quadratic least square approximation. So here we consider the set containing 3 elements, 1 t and t square. This is a linearly independent set. So by Gram-Schmidt process, we can find the orthonormal set corresponding to x1, x2, x3, u1, u2, u3. And by this theorem, if we have the orthonormal set, then Ym is equal to product x u1, u1 plus inner product x u2, u2 plus inner product x u3, u3 is the best approximation from span of x1, x2, x3 to an element x in H. So here also we take x as e raised to t, x equal to e raised to t, and inner product x u1, x u2 by as in the definition of inner product on L2, we can find all these values. Then what is the linear? First we consider linear least square approximation. So linear least square approximation is P of t. It is inner product x u1 u1 plus inner product x u2 u2. And a quadratic least square approximation is some q of t, inner product x u1 u1 plus inner product x u2 u2 plus inner product x u3 u3. This one. So instead of finding or instead of solving all the equations, n linear equations in M unknowns, instead of that, it is enough to find. If we orthonormalize the linearly independent set, simply we consider only this linear combination. Then here P of t and Q of t are the unique best linear and quadratic approximations from P1 or P2 to an element x equal to e raised to t. And we can see that the preceding examples, both the approximations are the same. So here, by this process, Q of t equal to this one, 3 minus 3 by etc. So this is similar to the Q of t obtained by using the preceding theorem. So I think this is easier. If we have a Hilbert space, then simply we can find, instead of solving the non-homogeneous system of linear equations, we can straight find the best approximations. So this is the concluding theorem. So let E be a non-empty closed convex subset of a Hilbert space. So if the subset we are considering is non-empty, is closed and convex subset of a Hilbert space, then for any x in H there exists a unique best approximation. So what we are going to do is, we are considering the closed subsets of a Hilbert space. So I am going to change this closed subset into a closed subspace. So all the subspaces of a vector space are convex set. So we can remove this one. So we replace this non-empty closed convex subset by non-empty closed subspaces of a Hilbert. So we are now dealing with closed subspaces. So I am considering this projection. So let H be a Hilbert space and Y a closed subspace of H. Closed subspace. Then we have the orthogonal complement of Y. It is elements in H which are orthogonal to Y. That means inner product Z Y equal to 0 for every. So the definition is set of all Z in H with Z is orthogonal to Y. That is a set of all Z in H with inner product Z Y. Orthogonal means inner product 0. For every Y belongs to Y. So that is the definition. So this is orthogonal complement. So if Y, then we have the orthogonal complement of any subset is a closed subspace of H. So Y is closed, its orthogonal complement is closed, and by projection theorem we can express the Hilbert space sum of Y and Y orthogonal with the Y intersection Y orthogonal equal to set 0. So this is a projection theorem. So if we have a closed set, then sum of the closed subspace and its orthogonal complement covers the whole space H. So the meaning of this is if you take any element X in H, then X can be expressed as a sum of the elements of Y and Y orthogonal in a unique way. So X equal to X in H equal to Y plus Z, where Y in Y, not X in Y, Y in Y and Z in Y orthogonal. So by using this expression, we can find the projection mappings, the unit best approximation relating to the projection. That's why. So this defines two maps, one P1 from H into Y defined by P1 of X equal to Y. So if we take any X in H, X has an expression like this, and first we project X onto Y, the elements of Y. That is the first projection. Since Y orthogonal is also closed, we project X onto the element Z. So we project H onto the second closed orthogonal. So we can find two projections. So first projection P1 from H into Y by P1 of X equal to Y. Second projection P2 from H into the second Y orthogonal by P2 of X equal to Z. Then by using the definition, we can show that this map is linear. So this is called the projection. P1 is called the projection of H onto Y. That is P1 of H is Y. And this is called the projection of H onto Y orthogonal. That is P2 of H equal to Y orthogonal. So a closed subspace Y of H, we can find. So what I am going to do is I am going to change this statement. Here it is a non-empty closed convex subset. We replace this by a closed subspace. So this, let Y be a non-empty closed subspace of a Hilbert space. Then for any X in H, there exists a unique best approximation from E to S by using that theorem. But the importance of this theorem is there is no need to find the approximation by using the 2 and 3 and so on. What we are going to do is by using projection, we can find easily the approximation. That is, this approximation is P of X equal to Y, where P is the projection of H onto Y. Because if we have a closed subspace of a Hilbert space, say Y, then H can be expressed as the sum of Y and Y orthogonal. Then one projection, there will be two projections, project H onto Y. In that projection, what is the image of X? That is the unique approximation from the closed subspace Y to X in H. So what we this is the first example. So we have this example. In the first example, by using the definition of approximation, we consider X and E, and we best approximation is X of 1, 0, 0. And by using this theorem, we are going to find the best approximation. So here X equal to Kn, X and E as in the preceding case, and here E is equal to span of the first element set E1, because E1 into etc. En is the standard basis of Kn. Then because all the components from second on are 0, so E is spanned by the first element 1, 0, 0, etc. So E is the span of set 1, set E1. Therefore, it is finite dimensional closed. And by the unique expression, x equal to E plus E orthogonal, E orthogonal is spanned by the other elements of the basis of x, E2, E3, etc. So span of E2, E3, etc. En. So that is also finite dimensional closed. So if we take any x in, we can write x as x of an E1, etc., x of an En. So y plus z, where y is the only the first component, first term, and z is the rest n minus 1 components or terms. So any x can be expressed in this form. Then we, by this definition, we can project x onto E and x onto E orthogonal. So if we project x onto E, that projection takes an element x in x to the element of y in, what is the y element in the set E. So here the element y in E is x of an E1. And what is x of an E1? X of 1 into E1 is 1, 0, 0, 0, 0. That is the n tuple. So if we multiply this, we get this approximation. And in the first case also, we get this approximation. So there is no need to find the infimum and all. We can straight away find the expression of x as the sum of the closed set and the orthogonal projection. Then take the projection, which takes x to E. That element will be the unique best approximation. And last problem. So we consider L2, the infinite sequence of with the sigma mod x of j square is finite. So let the y set of all elements in L2, alpha j in L2 such that alpha 2j equal to 0 for a variable. So alpha 2j 0 means the second component, fourth, sixth, even components are all 0. Then we can show that y is a subspace and it is closed. Then y orthogonal is set of all beta in L2 such that beta 2j minus 1 equal to 0. That is from the definition we have y orthogonal is equal to set of all x in H such that x is orthogonal to y. So it is equal to set of all beta j in L2 that for x such that in the product xy is equal to 0 for every y in y. And it is equal to set of all beta j in L2 such that in the product beta eta j equal to 0 where y equal to eta j in y. So it is set of all beta j in L2 such that what is the definition of inner product? It is beta j eta j bar is equal to 0. J ranges from 1 to infinity. And this y in y implies that eta 2j second components are all 0. So here we get a beta j in L2 such that second components are all 0 means sigma j equal to 1 to infinity beta 2j minus 1 eta 2j minus 1 orthogonal equal to 0. Because if j equal to 1, it will be beta 1 eta 1 bar. And j equal to 2, beta 3 eta 3 bar. Because the second all even components are all 0. So we get this. This is all elements in L2 with the beta 2j minus 1. So that is the orthogonal complement. So orthogonal complement is this one. And we have by projection theorem we can express H L2 as the sum of these two. That is, if you take any element in L2, that is gamma 1, gamma 2, etc., we can express this in this form: gamma 1 0, gamma 3 0. That is second component 0 and first component 0. The sum must be gamma 1, gamma 2, etc. So this is the unique expression: y plus z. First element is y, y in y. Even component 0, z in y orthogonal, odd component 0. So this projects H onto y. So let P1 is the projection from H into y. So P1 projects H into Y. So P1 of X equal to Y. So by using the preceding theorem, the unique best approximation from Y, the closed subspace Y, to an element X. We fix this element. Say X equal to gamma J in L2 is the element Y. That is the image of X under the projection which projects H onto Y. That is this one. What is the image? This Y is the first component. So this is the best approximation from Y to X. Similar way, if we consider instead of Y, if we consider Y orthogonal, then the unique best approximation from Y orthogonal to X, and Y orthogonal is the second closed subspace, and P2 is the projection from H onto Y orthogonal. H onto Y orthogonal. Then P2 of X equal to Z. And what is Z? Z is this one. So this is the unique best approximation from Y orthogonal to X. So similar way we can find the projections. That's all. The references are functional analysis by Limaye, and again introductory functional analysis theory and applications by Tracy. Any questions?
If any queries, participants can write your questions and doubts in the live chat box.
Avani, any questions from FB?
No, miss.
YouTube?
No.
Okay, Jeevan?
Yes, there is a question in
Oh,
Google Meet.
okay.
Sir, what is the best book to refer and study more on Hilbert spaces?
Many books are there, but if you are concentrating only on Hilbert spaces, you can find many. But if you want to study on Hilbert spaces, you just read Functional Analysis Limaye. It's the best book for functional analysis. But it is not that much easy to read that book.
Okay, sir. Thank you.
Thank you, sir. Thank you, sir, for your wonderful session. Jeevan? Jeevan, are you there?
Yeah, I'm here. A very good afternoon to one and all. Good afternoon, sir. Myself, Jeevan. I'm a second-year postgrad student. To be honest, I was really looking forward to attend this session, mainly because this session is handled by Shery sir. And, because I've been a student of Albert's before. Shery sir has been professor at Albert's for a very long time. And I used to be his former student. So today I'm feeling extremely proud and blessed to again attend this session yet again. So thank you so much, sir, for giving out this lecture exclusively for us. Also, coming back to the topic, I think this Hilbert space itself centers mostly on functional analysis. Anybody who have taken up a course on functional analysis would know how important Hilbert spaces are, especially its characteristics, the properties. Anything that revolves on Hilbert spaces finds a lot of relevance and application in functional analysis and algebra as such. So thank you so much, sir, for giving out this lecture. It was really informative. It was very productive and highly interactive. So I'm looking forward to attend more of the sessions, and I hope that all the students, all the peer members, all the faculties, and all the research scholars here have utilize this session to its fullest. So thank you so much, sir. And also one more thing, I would like to deliver my thanks on behalf of my friends, my college mates as well. I've also informed them about the session. I'm sure, I hope they'll be watching this session through YouTube and YouTube Live or Facebook. So I would like to thank you, sir, for being such a wonderful teacher back at Alberts and all. So thank you, sir, for being an inspirational and very phenomenal active member at Alberts. So I wish you all the very best for your future endeavors as well. Thank you, sir.
Thank you, Jeevan.
Thank you, Jeevan. I request you, dear participants, to fill the feedback form very carefully, given in the chat box. Please fill it very carefully. Now, I invite Dr. Jaya Els, Associate Professor of Department of Mathematics, to deliver the vote of thanks.
Thank you, Jess. Good evening, everyone. I am here to propose the vote of thanks for this webinar. On behalf of Maharaja's College and Mathematics Department, I would like to thank our Chief Guest and Resource Person, Dr. Shery Fernandez, Associate Professor, Department of Mathematics, Cochin University of Science and Technology, for enlightening us with sharing his knowledge. The talk was really informative and thought-provoking. I'm pretty sure that the knowledge Shery sir shared with us will definitely help us. Thank you very much, Shery sir. On behalf of Department of Mathematics, I acknowledge our gratitude to our principal, Dr. Matthew George sir, for giving us permission for organizing this webinar. I also thank him for his wholehearted support and guidance. Now, I thank Dr. Suja TV, Council Secretary and Professor of English Department for facilitating the event. On behalf of Department of Mathematics, I would like to acknowledge our gratitude to the IQAC coordinator, Sandur sir, for his strong support. Thank you very much. Now, I take this opportunity to thank Dr. Bloomy Joseph, Head of the Department and Convener of the webinar, and Professor Jismiri Jose, the Coordinator of the webinar series, for their selfless effort to make this event a great success. Now, I thank all faculty members of Department of Mathematics for their support in materializing the event. Now, on behalf of Department of Mathematics and Maharaja's College, I thank each and every participant for taking part in the webinar, cooperating with us for making the webinar a great success. Thank you all. Last but not the least, I would like to thank the team of research scholars and students, especially Sridevi, Avani, Jeevan, Kavya and Parvati for their timely action and selfless effort. Thank you, my dear students and research scholars. Once again, I thank all the organizers and stakeholders. Thank you, everyone.
Thank you.
Thank you, ma'am.
Thank you, sir.
Thank you all. Have a
Thank
nice day.
Okay.
Thank you, sir, for accepting our invitation.
Okay. May I leave now?
Okay, sir.
Okay. Thank you.
Thank you.